So last time we have studied relatively prime integers. If their greatest common divisor is 1, then the two integers are said to be relatively prime. Now we shall consider a result about this as Theorem 4. If two integers a and b not both 0 are relatively prime, if and only if. So instead of if, we shall consider let two integers a and b not both 0 are relatively prime, if and only if there exist integers x and y such that 1 is equal to ax plus by. So the statement we shall consider like this. Instead of let, we will consider two integers. Two integers a and b not both 0 are relatively prime, if and only if there exist integers x and y such that 1 is equal to combination of a and b. What is the definition of relatively prime integers? If the GCD of a, b is equal to 1, then they are said to be relatively prime, or no integer except 1 is common divisor of them. Example, we have seen GCD of 3 and 5 is equal to 1. Now what the theorem says that if these two integers are relatively prime, then they their combination can be expressed is equal to 1. So here the GCD of 3 and 5 is 1. Now 1 we can express in terms of 3 and 5. And how to express 1 in terms of 3 and 5? It is a and this is b. So we may write this as 3. 3 into some number plus 5 into another number. Now what should be the choice of x and y? We can see, we may consider this as minus 3 and this as 2. Then you see this becomes equal to 1. Minus 9 plus 10 is 1. So this is the property of relatively prime numbers or relatively prime integers. Now the property is if and only. That means if the two integers are relatively prime, then we can express this as 1 is equal to ax plus by, and conversely if we have x and y such that 1 is equal to ax plus by, then the two integers are relatively prime. That we have to prove. Now the proof. First, suppose two integers a and b, not both of them are 0, are relatively prime. Let a and b be relatively prime. If these are relatively prime, then GCD of them, therefore GCD of a and b is equal to 1. And this implies by theorem 3, if greatest common divisor of a, b is d, then d can be expressed as linear combination of a and b. So by theorem 3, there exist integers x and y. We have proved this result x and y such that 1 is equal to ax plus by, and this proves the first part. If the integers are relatively prime, then we can express 1 is equal to ax plus by. Now we shall consider the converse part. That is, conversely, suppose there exist integers x and y such that such that 1 is equal to ax plus by, and let the GCD of a and b is equal to d. Now what we have to do, if we have assumed this, we have supposed this 1 is equal to ax plus by, we have to prove the two integers are relatively prime, and when the two integers are relatively prime, if their GCD is 1. So we have to prove d is equal to 1, then a and b will be relatively prime. Now GCD of a and b is equal to d. What this implies, d is common divisor, so d divides a and d divides b. And if d divides a and d divides b, d divides the combination of a and b. So therefore this implies d divides ax plus by. So whatever x and y may be. And d divides ax plus by, this is by theorem 1. You refer theorem 1, or it is not 1 but 2. Theorem 2. And if d divides ax plus by, but ax plus by is 1, so this gives d divides 1. And again this implies mod d is less than or equal to modulus of 1. Theorem 2. We have proved these results in theorem 2. And because d is greatest common divisor, it is positive, 1 is positive, and therefore this implies d is less than or equal to 1. And again you see this will imply d is equal to less than or equal to 1. But d cannot be less than 1, because if d is less than 1, it is integer, it must be 0. And GCD is not considered to be 0. So therefore this implies d is equal to 1. Since d is positive integer, d is a positive integer, and therefore d is equal to 1 means GCD of a and b is equal to 1. And if GCD of a and b is 1, therefore a and b are relatively prime. So this proves the theorem. So we have proved the result in two ways. P implies Q and Q implies P. So this completes the proof. Now we shall consider a corollary to this result. Say, let GCD of A and D is equal to D, then GCD of A divided by D, D divided by D is equal to 1. This is usual division. A divided by D means A upon D, B upon D is 1. So this we shall do. Now we note that this A by D is not a fraction, it is an integer, because D is divisor of A means A is multiple of D. So therefore this is not fraction. Now and then we have to prove these are relatively prime. That means A by D and B by D are relatively prime. So an example can be considered like this. You see. We have GCD of 4 and say 8 and 12. What is the greatest common divisor of 8 and 12? That is 4. Like this, we verify this theorem. And now what is the result means A divided by D. Here 8 divided by 4 and 12 divided by 4. So this is GCD of, what is 8 divided by 4? That is 2. And 12 divided by 4 is 3. And what is the GCD of 2 and 3? They are relatively prime. No number except 1 is common divisor of these two. And therefore it is 1. So this is the meaning of the theorem. Now the proof. GCD of AB is D. So therefore this implies D divides A and D divides B. We shall first state that these are integers, and that is A and B are multiples of D. Therefore A divided by D and B divided by D are integers. You check by this example. These are integers, 8 by 4, 12 by 4. And further, now we have to consider the GCD of A by D, etc. Now since GCD of A and D is equal to D, we can write there exist x and y, two integers x and y, such that this is by theorem 3, such that D is equal to ax plus by. Now we divide both sides by D. So this is dividing both sides by D. So what we shall get is 1. 1 is equal to ax plus by. And if there exist integers x and y such that ax plus by is equal to 1, so what this shows that this is not only ax plus by, we have to divide both sides by d. So this is 1 and this will be a by d into x plus b by d into y. So this shows that the linear combination of a by d and b by d is 1, means a by d and d by d are relatively prime, or their GCD must be equal to 1. So this shows that by theorem 4. So this is for your reference, by theorem 4, GCD of a by d and b by d is equal to 1. Hence the corollary. So the illustration is this one. Now we consider this as a corollary 1, and now we shall consider corollary 2. If A divides C, B divides C, and GCD of AB is equal to 1, then AB divides C. So this is the result that we shall prove as corollary 2. First, what is given is A divides C and B divides C. Write the proof for this. Let A divides C, B divides C, and use the definition of divisibility. If A divides C, C is multiple of A. So therefore there exist integers, or we can write directly as a C is equal to, this implies C is equal to A into R, or some integer R, and C is equal to B into S for some integers R and S. Definition of divisibility. If A divides C, when we say C is equal to multiple of A, means A into some number R. We are considering R and S here instead of X and Y. So for some integers R and S, we refer this as 1. Now it is given GCD of A and B is equal to 1. Consider this. Next, GCD of AB is equal to 1. So what this will imply is 1 is expressed as combination of A and B. So therefore there exist integers x and y such that 1 is equal to ax plus by. Now finally what we have to show is AB divides C. C is multiple of AB, that we have to show. So therefore we multiply both sides of this equation by C. Multiplying by C, so what we shall get? C is equal to 1 into C, and that means C into ax plus b1, or you see further this is equal to C into ax plus C into b1. And here we shall use equation 1. Now what is equation 1? Here it gives two values of C. C is AR and C is also BS. So here it is a C AX. Now we use the value of C as BS here because we want AB as common. So use this value C of is equal to BS first, and then use this value of C is equal to AR in the second term. Or you write this as BS and this as AR. So this implies C is equal to left side is C, and the value of C we shall not use AR because it will be A square. We don't want A square, we want AB, therefore use this value BS. BS into AX plus, and here we use this value of C AR B1 by 1, and now we can take AB common from this, and that is C is equal to AB. If you take AB common from the right side, then here what remains is Sx plus Ry. Now yes, all are integers. A, B, X, Y, S, R are integers, so this is an integer, and the C is written as AB into some integer, means C is multiple of AB, and C is multiple of AB means AB divides C. This shows that AB divides C. So this proves the second problem. Now next we will have theorem number 5 as Euler theorem. Let A divides B, or A divides B into C. A divides B into C, and GCD of AB, or we name this theorem as first Euler theorem. Euler's theorem. If the statement is now, if A divides BC and GCD of AB is equal to 1, then A divides, yes, A divides, this is the name. We shall consider first the earlier corollary we have proved is this one. A divides C. A divides C and B divides C, and we have GCD of AB is equal to 1, relatively time. Then AB divides C. Example of this, you can consider example to understand the result. Now, for example, I shall consider say 2 divides 6, and also we will consider 3 divides 6. See, A divides C, B divides C. A is taken as 2, B is taken as 3. And whether GCD of A and B is 1? Yes. GCD of 2, 3 is equal to 1. No number common divisor as for 2 and 3 except 1. So this satisfies the theorem's condition. Then what this must show that A into B must divide C. That is 2 into 3 must divide 6. 6 divides 6. That is 2. Or any other example you may consider and verify this. So this result. So taking example, you should verify the results. Now what is the meaning of this result? A divides B into C, and the GCD of A and B is 1, relatively prime, then A must divide C. So this we shall do. So write the proof for this. First we shall consider GCD of AB is equal to 1. And this will imply there exist integers x and y. Theorem 3, such that 1 is equal to ax plus by. Now what we want to show, A divides C. So we want to show C is multiple of A, means we want to express C as A into some number. So we want the expression for C, and therefore we multiply this equation both sides by C. Multiplying both sides by C, what we shall get? C is equal to, and right side is C into ax plus by. Or this will imply Cax plus Cby. Therefore, C is equal to Cax plus C into by. And we want A as common now. Now we have A divides AC. Now you see, A divides AC. This is obvious because AC is multiple of A. And secondly, it is given A divides BC. This is given in the theorem. And what the together implies, A divides AC, B divides BC, means A divides combination of AC and BC. So this implies A divides ACX plus BCY. Combination of this. Theorem 1. You see the corresponding result. It may be fourth result. If A divides B and A divides C, then A divides the combination of two integers. And what is the ACX plus BCY? You see it is, so, or we may refer this as 1. And this implies A divides C by. And this is what we wanted to do. This proves the result, hence the result. Now an example for this. You observe A divides B into C, but these two are relatively prime. For example, I can consider like this. 5 divides 3 into 10. Obvious. And what is the greatest common divisor of A and B? Means 5 and 3. And GCD of 5 and 3 is equal to 1. See the verification of this. And therefore this must imply, if this does not divide 3, this must divide 10. So this implies 5 divides 10. It is obvious. So A divides C. So this is an example for the result. So this proves the Euler's theorem. You should verify each theorem you considering examples satisfying the conditions. Now one more theorem we shall consider is about the greatest common divisor. So we write that as next theorem. Let A and B be integers, not both 0. Then GCD of AB is equal to D if and only if. if and only if there are two conditions. A divides D, not like this, D divides A. D is divided, so D divides A, D divides B. And second, if C divides A, C divides B, then C divides D. So actually this is the definition of greatest common divisor. There we have C is less than or equal to D. Here we have C divides D. This we have to prove. Now the proof. Proof will contain two parts again, if and only if condition is there. So that means if GCD of AB is D, then we have D divides A, D divides B, etc. And second, these two conditions must satisfy. And conversely, if these two conditions are satisfied, then GCD of A and D must be D. So we can consider the first part. Let GCD of AB is equal to D. So what this will imply? This implies D divides A by definition and D divides B. So and what is the second? So this is the one holds. So this is by definition. Therefore, one holds. One is true. Now what about the second? See, if D is the GCD of AB, if C is a positive common divisor of A and B, that is C divides A and C divides B, then so we have to show that C divides D. Then you may say C will divide the linear combination of A and B. So then this implies C divides AX plus B1. Now, because the GCD of AB is equal to D, therefore some choice of X and Y. But GCD of AB is equal to D. So this implies by theorem 3, there exist integers X and Y. Such that D is equal to AX plus B1. Now we put this value of AX plus BY as D. So therefore, we may suppose this as 1. Therefore, by 1, C divides D. And this gives the second condition, hence second holds. Hence, 2 holds. So that means if GCD of A and B is D, then 1 and 2 holds. Now the converse part. Conversely, suppose 1 and 2 holds. Suppose 1 and 2 holds. Now what we have to do? We have to prove that GCD of AB is equal to D. Greatest common divisor of A and B is equal to D. This we have to prove. Now see, first condition is the same. D divides A and D divides B. That is given. So the one holds. Now only we have considered if C divides A, C divides B. So it is by 1. D divides A and D divides B. Now by 2, if C divides A and C divides B, then C divides D. That is the second condition. So by 2, C divides A and C divides B implies implies C divides D. So therefore here we must have C. If C divides D, then mod of C is less than or equal to mod of D by theorem 2. The left side number is less than or equal to right side number, absolute value. And because C and D are positive, we have considered C is positive common divisor. So this implies C is less than or equal to D, since C and D are positive. And thus C is smaller than or equal to D, means D is the greatest common divisor. We have considered, we have proved this GCD of AB is equal to D. So this proves that. This proves the condition in the definition. What is the definition? When we say GCD of AB is equal to D, D divides A and D divides B, and second condition is C is less than or equal to D. So this proves GCD of A and B is equal to D, and hence the proof. So this completes the proof. So these are about some theorems on relatively prime integer and greatest common divisor. So next time we shall consider problems from the exercise.